Chapter 3, IT hardware and software. That's where we're starting. Mostly IT hardware in this chapter. And as you can imagine, it's a very difficult chapter to talk about. It's a difficult chapter to write and put in a textbook unless you're going to be updating your textbook every 6 months, which they don't do for cybertext. So we'll talk about it just to give some context, but we'll go also stray a little bit from the text because I think if you got too focused on the text, you'd be talking in 2009 terms, which isn't necessarily where we want to be. So we'll talk about hardware and software. Hardware breaks down into 4 subcategories that are really blurred when you get down to it. An input device is also an output device. A data storage is really an output device. It all kind of blurs together in the modern world, but we'll talk about it. And then we'll just very briefly talk about how software works. Okay, so we think about the components of a computer. We saw on Monday, it's really input, process, output in some form. That's how all computer systems work. Input devices, we have some examples of input devices here, some examples of output devices here. You have your CPU, and then you have storage devices and communications. We'll have a separate chapter, probably the most difficult chapter to talk about in this class, which is telecommunications. We'll talk about it briefly. It's not central to what we're trying to accomplish here. But that's chapter 4, which we're not going to do next. Okay, input devices. There's older technology and newer technology. The newer technology serves the purpose of trying to minimize human involvement. Because the more human involvement you have, the more mistakes are possible and the more time that it will take. Because humans make mistakes and humans are slower than the speed of light, which is how fast computers work. So we try to minimize human involvement with newer technology for input. So the textbook talks about some technologies, and they're all good, and we'll talk about them in a moment. I would categorize technologies in a few categories. There are what we'll call discrete input devices. These devices are like keyboards. You type something in, and it does a specific thing. Type in the letter A, and it processes the letter A. You have pointing devices, like a mouse. You have imaging devices, like a camera or a scanner. Or I play a lot of golf, the range finder, that tells, laser, tells you how far away you are from something. That's an input device. And then you have audio devices, like a microphone is an input device. So those are kind of the categories. Within that, some kind of technologies. You have the older technology. I talked about when I would be a key punch operator when I was in college. That you did it off of source documents, paper. So paper could be an input device that you then have to do something else with. OCR, optical character readers. It takes, let's say, a PDF file. You ever seen something that will take a PDF file and turn it into Microsoft Word? It reads the characters and then turns it into digital form. It's reading something that's an image and turning it into a digital form. Plastic cards with magnetic strips. What are these things? credit cards, this thing, magnetic strips. When I walk into this room, I swipe. It tells the technology department I'm in here. It tells the technology department, there's an input device back there watching all you guys. So I can go and check who's on Facebook right now, later. So that's, and of course credit cards are, and there are tons of new things. Digital cameras, GoPros, whatever. Biometric scanners. Iris scanners are a better technology than fingerprint, more precise. A more precise print of who you are. Anyone see that movie? What was that movie with Tom Cruise? Minority Report, where he took someone else's eyeball to get into a secret area using an iris scanner. That's not going to happen a lot in the real world. Sorry I mentioned it. So these are some examples of technologies used for entering data. MICR. You probably have seen these numbers on the bottom of your checks. It's actually magnetic ink. Those numbers. And they tell a story. They tell a story. About where it's coming from. And then optical scanning. The old barcode. You've all seen this, and I'm sure most, if not all of you, have seen this. Anyone know what QR stands for? Quick response. Quick response. This stores a whole lot more data. The quick response QR reader stores a whole lot more data than a barcode. A barcode, essentially, these bars are just producing these numbers. You could almost see here, this one, and this one are exactly alike. They're the number 0. And then this larger number means something. Tells you what the item is. But the QR reader, you've seen them, subway stations. If you go over to Europe, they're all over. They can connect you directly to a website, right? They're much more robust in terms of what they can store. Point of sale systems. Whether you're going in through Amazon and ordering something, or you're at Walmart and they scan using a barcode, or you're at McDonald's and they press a button that says you ordered that Big Mac. The point of sale system does a lot. Here, it's a great example of how you minimize human interaction through the input process. For Amazon, the fact that you're doing the data entry, if you made a mistake, it's your mistake, right? For Walmart and McDonald's, the fact that they're scanning it or pressing a button, the button has more error possibility than the scan. That scan has a lot of information. It determines the price. So you could change price on the fly. You can ensure that somebody's not undercharging or overcharging because the price is set. It records revenues. So for your cash management system, you can see real time where you are in cash. And it updates inventory. So it decrements one from what you have on hand. If you have a just-in-time system, it can automatically trigger a reorder if you reach a threshold point. So a point of sale system is a very powerful input device that results in a lot of things happening in real time. That's it for inputs. Anybody? I didn't think of all the inputs. Anybody have some inputs I didn't think of? There are a lot of them, right? Everything, your phone's an input. the processor, the CPU, the guts of the computer, has a few different components. Any one of these components could become a bottleneck. So as you buy a CPU, you kind of want to manage these bottleneck areas. You know, RAM is definitely a bottleneck. The clock speed, the I/O bus, depending upon what you're doing, are all bottlenecks, and I'll explain what they are. So the clock speed, that's just what it sounds like. That's how fast your CPU works. Okay? The clock speed is something that has dramatically increased over the 50 years of a computer. Maybe you've heard of Moore's law. What is Moore's law? It's it gets faster and faster. 2 years is what they usually talk about, but it doubles every 2 years is Moore's law. And it has been doing that for 50 years. Now, it's not a physical law that says that's going to happen, so it can't happen forever. But so far, it's been true for 50 years. They're talking about it maybe slowing down around 2020, where they're just going to hit some physical laws that are going to prevent it. Because the speed is really how quickly the CPU can oscillate between zeros and ones. That's the speed of a CPU, because it's all about bits, right? As we talked about last time. So the speed of that oscillation, at some point, hits some kind of a wall. But using new materials, creating smaller spaces, they're able to continue to do it, to speed it up. Microprocessors and flow of data. The control unit. This is kind of the brains, the central nervous system of your computer. This is what kind of tells the rest of the computer what to do. Well, let's go to the hard drive and grab a piece of data. It's kind of the part of the computer that controls all other activities. It's the central nervous system. The ALU, the arithmetic-logic unit, does the calculations. 2 plus 2 equals 4. So the two of these are really the brain and the central nervous system of the computer. Cache. There are really 3 definitions of storage when you think about a computer. There's cache, there's RAM, and then there's hard drives of some kind. The cache is what's actually right there, right in the middle of your CPU, a relatively small amount that is used to do your arithmetic. It'll store the number 2 and the other number 2 and figure out 4 for you. So that's your cache. Your RAM, which is something who's bought a computer recently? Anybody know what RAM is, the normal RAM they sell? 8 gig of RAM. You want to get as much RAM as you can afford, essentially. Because what RAM does is it takes data from the hard drive and stores it in your CPU. And if you have 8 gig, that's 8 gig of data you could store there, and it's less going out and back and forth to the hard drive. So the more RAM you have, the less it has to physically go out to the hard drive to get more data. And with the newer operating systems, I know Windows 8 was famous for this. It grabs a lot of the RAM itself. And I think iOS 8 also. Is it iOS 8? Yeah. Grabs a lot of RAM. So it leaves less for if you're using Microsoft Excel. You want to bring Excel into your RAM as well. So you don't have to go back out to the hard drive as much. Things will be faster. So that's why you want as much RAM as possible. The I/O bus is kind of a tube. Think of it as a tube. It's the highway between your CPU and your storage devices. So you want to have the fastest tube, the biggest tube to do it. So you you want to have an I/O bus that can get the data into RAM in case you need to go out there regularly. Listen, I remember when I first started using Microsoft Excel, years and years and years ago. You'd hit enter, and it would take a minute to do a calculation. It would just churn. And it could be doing this and going out there. Now it takes a fraction of a second to do the same calculation. Times have changed. So that's more or less what a CPU is composed of. And the good news, this stuff is getting so fast, it's almost becoming irrelevant. So, output devices. The text really differentiates output from input devices. In today's world, they kind of come together to some degree. Output devices are also input devices, but a printer is clearly an output device. And I think the text still talks about dot matrix printers. Not anything you need to think about, except that since you randomly get a quiz, right? Chapter 3 quiz, you may have a question on dot matrix printers. It'll be there somewhere. But printers are an output device. Various multimedia devices, your screen, your phone, etc. Then you have storage. Oh, I'm sorry, still going to talk about printers, so whatever. When you think about screen displays, you do care about a couple of things, and mainly if you're a gamer. How many of you are gamers in here? Okay. So you know this more than me. The refresh speeds and the speed of your monitor matter to you if you're a gamer, because you want to have the fastest possible for that kind of thing. For the vast majority of us, you don't need that. But if you're a gamer, you're going to care about this kind of stuff. Which video card your computer has in it. Of course, it'll be faster for you. It kind of refresh speed for when you want to display. Data storage. Data also goes by Moore's law. You double the amount of data you could store on a given piece of hardware every 2 years or so. Right now, I was just at the Apple store the other day, and I saw something called an external drive, and you could buy for about $79 an external drive that will store a terabyte of data. A terabyte for about $79 an external drive. Let's think about what a terabyte is. We start off with a bit, right? 8 bits make a byte. So you have 1 byte. Then you have a gigabyte. A gig. How much is a gig compared to a byte? 1,000. 1,000? No. A kilobyte. A billion. A gigabyte. A billion bytes is a gigabyte. A billion bytes. So if you have a gigabyte of storage, you can store 1,000 letter A's. A billion letter A's. A terabyte is 1,000 gigabytes. So if you have a terabyte of storage, you could store 1 trillion letter A's. And that's where storage is now. A terabyte. And it's about this big. Anybody know what the next one's called? 1,000 terabytes, what it's going to be called when we get there? Anybody know? Anybody know what it's going to be called? A peta, that's a P. A petabyte. A petabyte. Can't even imagine what you'd store. It's 1,000 terabytes called. You know what? If you would have asked me 10 years ago, what could you store in a terabyte? I wouldn't have thought about it. But then you all start taking pictures of your food and storing that. So who knows? You start taking videos of your food, and you know it all. What happens in real life, as you create the possibilities, the results are, you know, you can't even imagine what you're going to do, because the possibilities are out there, right? Okay. So, I mean, the text talks about magnetic tapes. That's really old technology. It's sequential, right? A tape. It's like if I used to listen to tapes when I was younger, tape drives. But actually, people still use magnetic tapes for backup purposes. So if you're, go to my old company, Goldman Sachs, and you want to store all your data and then send it off to the mountains of Utah and store them in a mountain in case of an apocalypse, but you still have that trade data. You put it on tape and store it. Because there's not a real lot of knowledge about how long, because this is physical storage, how long non-physical storage, just kind of digital storage is going to last. So it's done on tape. The only real reason. Hard drives, we all know what that is. They've taken different shapes. When I was younger and we were starting out, they were looking at different shapes for how do you maximize the surface area, because hard drives are all about surface area. Do you have multiple drives? They used to be they used to be magnetic drums to try to maximize the surface area and minimize the physical motion. That's what you want to do with a hard drive. So now we've pretty much come up with really small drives. And of course CD and DVD drives, which are good, but they're really almost not used anymore, right? How many of you have watched a DVD in the last year? Really? I haven't. Yeah, this is Netflix. These are ways to get at the data, right? And if you buy software, very rarely do you get it on a CD. Most of the time now, to make computers smaller, they don't even include a CD drive anymore on the computer. Okay. There are a couple of things to know about RAID. RAID is the concept, and these are very old. They look different now. The concept of having multiple drives together, not for the purpose of increasing your storage capacity. It's for the purpose of creating fault tolerance. Fault tolerance. So when you write some output to a drive, if you wrote it to one drive and that drive were to fail, you've lost that data. But if you wrote it to 3 drives and one drive fails, you have other copies of it real time. So RAID, when you have RAID, generally you have an odd number, call it 3. If 2 agree and 1 is different, the one that's different is considered to be a problem and taken offline, and the other 2 will suffice until you can fix the problem one. So RAID is used for the purpose of fault tolerance, not to increase storage capacity. Multi-platter hard drives, as we've talked about, physical motion is kind of the worst thing. And what happens with a hard drive is a head reader, is pointing to a place on the hard drive to grab the data. So if you have multiple platters, one above the other, with enough room for the head to fit in between, and if the computer is smart enough to store your data in a certain way so that the same physical motion can get at 3 different pieces of data that are closely related, you will then reduce or minimize the amount of head motion. Now, as you're storing more and more data on a smaller unit, this becomes less and less relevant. And we all know about flash drives. Who still owns a flash drive? I do. I haven't figured out how not to. Who's replaced flash drives with the cloud in some way? Yeah, I haven't gotten comfortable with that yet. I'm old. But you can replace a flash drive with the cloud, somebody else's storage. A cloud is just a hard drive that somebody else is letting you have access to. Okay. The acronym's POS, MICR is really MICR, and OCR are most closely associated with which of the above? Yell it. A, B, C, or D? A. They're all input devices. Okay. Which of these is capable of storing the most data? I have not said it, but it should be fairly straightforward. D. It's bigger than a flash drive, just physically bigger. And these things are just lower quantity storage devices than a hard drive. So that's D. Okay, that's it for hardware. Unless you have any questions on hardware. It's just a type of storage drive. It's the way that the it interacts through the I/O bus to the CPU. SATA is it's one of many. So if you have a computer that's expecting one of those, then if you put a different kind of drive in, it's not going to work, right? Software. We're just going to go over software pretty quickly here. We'll have a separate chapter to really talk about databases, and because that's the heart of what we're really talking about in this class is database management systems. So we're not going to focus on it today. Operating systems. Microsoft, Apple. The operating system is kind of the brains from a software perspective. It decides how to allocate resources, how to write data. So the operating system controls all of the other software that's running on your computer. 3 concepts. I'm not going to differentiate. All 3 are going to differentiate multiprocessing from multitasking and multiprogramming. I'll keep those because the difference between multitasking and multiprogramming is very subtle. Multitasking is what we do. We multitask. We all think we're able to do lots of things at one time, but we're not. So we just time slice. Oh, I'll listen to Professor Cooperberg now, but now I'm going to send that text I needed to send. I'll listen to him again and hopefully fill in the blanks in my brain between those 2 moments of listening to figure out what I missed. That's multitasking. And the more multitasking you do, when you go here, 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 the more scattered you are, the more kind of slow things are actually happening. But we're not, when we're multitasking, actually doing 2 things at once. We're doing one thing at once and then doing the other thing and coming back and going back and forth. That's what most computers do. They multitask. Multiprocessing, on the other hand, if you have like a dual core or whatever, you're actually doing 2 things at once. And that's the difference. It's able to do the calculations for one program and do something else for another program. Different processors doing the same things, doing different things at the same time. sometimes called parallel processing. How many of you saw the movie The Imitation Game? Anybody? Just one? It's an excellent movie. I should make it a requirement in this class. Because he really invented, in that movie, the first computer. If you want to see what a really slow computer is, back in the 1940s, that's what he did. He created the first computer. And it was really, it went from there. And you see how big it was and how little it did, and you'll really get to see Moore's law in action. So we'll talk about how you convert something called source code to object code. First, let's define object code. Anybody know what object code is? Object code is what a computer can read. And what can a computer read? Zeros and ones. All the computer knows is zeros and ones. Now, obviously, when we write code, we can't write code in zeros and ones, although at the very beginning they had to. We write code more and more in something that looks almost English-like. Then it has to go through some steps from English-like to zeros and ones. So source code is English-like, and object code is zeros and ones. And the process of getting from here to here is called assembling and compiling. Debuggers, it's a different category. Debuggers are tools that help you when you're writing code to figure out why you have bugs, why you have problems in your code. They kind of like take the pathways your code is going and look for problems for you. That's what a debugger is. And you guys are going to have some bugs. Okay, so the very first generation of programming languages were written in machine language. Essentially, you wrote the object code. So these first computer guys were really, and women, were really smart because they had to write in zeros and ones. The second generation wrote in assembly language. Assembly language. Not quite English, but at least you could kind of see a logic in it. Then the assembly language would have to be assembled into object code. The third generation of programming, which is the generation I learned how to program, felt kind of English-like. It wasn't perfectly English-like, but it felt kind of English-like. I first learned COBOL, which is more or less a business language. Fortran and Pascal are more scientific languages. Visual Basic, Java, and C and C++. People are using those today. Kind of closer to English language and meant more for smaller computing systems. These were meant for the old big IBM mainframes. So when you have a third generation language, it has to be compiled into assembly language and then assembled into source code. So a compiler is the first step to getting it to machine language. Interestingly, so if you work for a company that buys a software package, or if you're buying Microsoft Excel, which is probably written in some kind of a third generation language, what's on the CD when you buy it, or what's shipped to you, is not source code. They send you the object code. Anybody know why they would send the object code? So that you don't steal it, essentially, right? They give you the source code, then you have control. So when a company is buying software from SAP or someone else, generally speaking, they buy the object code, and then if you do your contract right, you make the point that should SAP go out of business, you would get access to the source code, so you can continue to use the software. But they don't want to give you their source code. That's their jewel, their crown jewel. They'll give you the object code to work with. Fourth generation languages, which is kind of where we are right now. And Microsoft Access would qualify as a fourth generation language. It's not procedural, it's not transaction based. It feels very English-like. You can do a lot of programming simply by pointing and clicking, which is how we're going to learn how to program, pointing and clicking. What Microsoft Access does is it goes from your pointing and clicking, and it creates SQL, Structured Query Language, which is truly the fourth generation language. So behind the scenes, it's converting your point and clicks into a language, which is then compiled and then assembled and then available for processing. Object-oriented programming is really not on this path. All it is a style of programming that you do right now and which you're going to do in this class, which rather than being transaction-based, it's object-based. Events, things, and how they relate to each other. And this became popular back in the 90s as the model to use, the 1990s. So as I said, it starts with source code. That source code is compiled, assembled, and then it becomes object code. And the object code is what you buy when you buy off-the-shelf programs. Not going to talk too much about software here. Their software fits into two categories, general purpose and special purpose. General purpose is what we've always thought of: word processors, spreadsheets, database software. And special purpose software are things like QuickBooks or any application software that's used for a specific user purpose. Your chapter will spend a lot of time on what are the attributes of various configurations. That time that they spent was out of date 3 months after they did it. So we'll talk about the various configurations, but I don't care at all. Don't get caught up in a supercomputer processes at a certain speed and has so much storage. It changes quicker than a book can possibly stay up to date with. But the largest computers are supercomputers, Cray computers. These do multiprocessing. If you think about the NSA looking at every bit of data and every bit of, every bit of data, let's stick with that, that's passing through the ether. They're using supercomputers to look for trends and look for problems. But you think about that, they're probably going through a petabyte of data a day. Then you have mainframe computers, still used by large companies to process their business. IBM is the historically major provider of mainframe computers. So accounting systems would generally run on something like that for a large company. Mini computers. These kind of have been squeezed out a little bit in the real world. So they're smaller than a mainframe, larger than a server. Used to be things like a DEC VAX, names that I remember, used maybe by a department of a company to process their specific needs. Would be done on a mini computer. Then you have servers, which are really just very fast and powerful workstations, which are just very fast and powerful PCs. A server doesn't really need a monitor. No one's looking at a server. It's just a processor. It could be a data server. It could be a print server. It could be the server that's used to filter all the traffic that comes into Rutgers to make sure that none of it is going to cause a problem. It could be, a firewall of some kind. A workstation is a powerful personal computer, maybe used by somebody who's doing CAD/CAM. And we know what CAD/CAM is. Computer-assisted design. So an architect might use computer-assisted design. And then personal computers. How many of you have a PC? I do too. How many use your PC more than you use your tablet? You do? Okay. I'm kind of half and half now. Certain things tablets don't do well. So this is what our text talks about. Now let's talk about the real world. That's just the beginning of the story. It goes to tablets and smartphones and televisions. Your thermostat now is computer-based. This connected world, everything is a system now. A chip. Really, all you need to have a computer now is a chip. So I think it's more important to think about it with all of the devices.